Okay, today we're going to be talking about chapter 8, which is about rotation. And you'll see as we go through that rotational motion that we're going to be dealing with, we're no longer using feet or meters. We're going to be using angular measures such as degrees, revolutions, or radians. And these quantities can be converted just like you converted feet and meters. So what we see, and this could be just a little review for you, that remember there's 360 degrees in a complete circle. 1 degree is equal to about 1 over 360, which is around 0.0028 revolutions. There's also this term that's called the radian, and the radian is defined as the angle for which the arc length along the circle is equal to the radius of the circle. So this would be your radian right here. There are approximately 2 pi in 6.28 radians in this complete circle. So a radian is a little larger than 57 degrees. 1 revolution is 2 pi radians. This is going to be a conversion factor that we will use during this chapter. Also keep in mind that radians are unitless. There's no units associated with them. Another thing to keep in mind is that revolutions is an angular quantity, whereas radians is a linear quantity. So what I've done is put together this little chart for you where we have linear motion, circular motion, and the units for the circular motion. So here we have, instead of saying or using x as a position, we're now going to be using theta. Our velocity is now going to be omega, and that's going to be delta theta over delta t. And those new units we're going to use are radians per second or revolutions per minute that we typically abbreviate RPM. Our acceleration is going to be denoted by the symbol alpha, and alpha is going to be delta omega over delta t. And those units are radians per second squared. So let's look at a few problems. So in this one, we have an automobile engine that is described as operating at 5,000 RPMs. So we have 5,000 RPMs, which if you remember, that means we have 5,000 revolutions per minute. And you're asked to express the velocity in radians per second. Well, we go back to our conversion factor from the previous slide, and we saw that in 1 revolution, we had 2 pi radians. So our revolutions cancel, and we're going to be left with revolutions per minute. But notice here you're asked for revolutions per second. So we must also convert our time, and we know in 1 minute, we have 60 seconds. So when we punch this into our calculators, we should get a total of 523.4 radians per second. So you don't want to forget about that time value also. Now the next problem, we're looking at a CD, and that CD spins at a variable rate between 500 and 200 revolutions per minute as it plays from the inside track to the outside track. We're told it contains 60 minutes of music, and you're asked to find the average rotational acceleration. Well, our omega F is going to be 200 RPMs. Our omega initial will be 500 RPMs. Our delta T we're given as 60 minutes. And you're asked to find alpha. Remember, alpha is delta omega over delta t, which is omega final minus omega initial over delta t. So we have 200 RPMs minus 500 RPMs, and we're dividing that by 60 minutes. So that's going to give us a alpha of -5 revolutions per minute. And that is per minute squared because we're dealing with acceleration. And the minutes from here actually are on the bottom because it's revolutions per minute. So we have minute times minute, which gives us our minute squared. The next one, we have a flywheel that's originally at rest. So therefore, we know omega initial is going to be 0. And it reaches an angular velocity of 36 radians per second. So omega final is 36 radians per second. And the time it does this is 6 seconds. And you're asked for alpha again. So alpha is delta omega over delta t. So we have 36 radians per second minus 0 divided by 6 seconds. And that's going to give us 6 radians per second squared. Another problem, we have a roulette wheel originally turning at 0.80 revolutions per second. So we know that's going to be our omega initial is 0.80 revolutions per second. It coasts to a rest in 20 seconds. So our time is 20 seconds. And you're asked for what's the acceleration of the wheel. And you're also asked for how many revolutions it turned. So if it coasts to a rest, then we know the final, omega final must be 0. So we have alpha is going to be omega final minus omega initial over delta t. So that is going to give us 0 minus 0.8 revolutions per second divided by 20 seconds, which will give us negative 0.04 revolutions per second squared. And now we want to find delta omega, or delta theta, excuse me. So we have omega equals delta theta over delta t. And we can rearrange that to be delta theta equals omega times delta t. Well, we have our omega as 0.80 revolutions per second, and we're multiplying that times 20 seconds. So our delta theta is going to be 16 revolutions. Okay, now just like our translational velocity and acceleration, our rotational velocity, rotational accelerations, they're also vectors. When we go to assign direction to the rotational vectors, it's not going to be quite as obvious as it is for the translational ones. The only directions associated with the rotating body that are not continually changing are the direction of the axis of rotation. So what we're going to do is we're going to assign the direction of the rotational velocity to be along the axis of rotation. So what we're doing is we're assigning the direction of the rotational velocity to be along the axis of rotation. So by convention, if you curl your fingers, you want to use your right hand along the direction of rotation. As you can see, the direction of rotation coming out of the top. So you take your fingers, you curl it around. Your thumb is going to point along the axis in the direction of rotation. This is what we call the right hand rule. So you can see our axis of rotation is pointing up because that's the direction our thumb is pointing. Now, the direction of rotational acceleration is also along the axis of rotation. So we can see two cases in this figure, one for speeding up and one for slowing up. So if we're speeding up, the angular acceleration is in the same direction as the angular velocity. So here's our angular velocity, here's our angular acceleration. They're both pointing up. However, in the picture on the right, we're now slowing down. Notice the angular acceleration is now pointing in the opposite direction of our angular velocity, which indicates that we are all slowing down. So let's look at this problem. So in this one, you're asked to find the rotational velocity, magnitude, and direction of the second hand of a wristwatch. Okay. So, well, think about a wristwatch, not an Apple Watch, an actual watch that has the clock face, not digital. So the second hand makes one revolution. So it makes one revolution each minute. Goes around one time every minute. So basically, 2 pi radians every 60 seconds. Okay. So omega is going to be 2 pi radians every 60 seconds. So 2 pi radians, 6.28 radians divided by 60 seconds, and we get 0.105 radians per second. Now, remember, direction of your rotational velocity is going to point along the axis of rotation. So in this case, the axis of rotation is into your wrist if you do the right hand rule. Okay. Remember our right hand rule that we looked at. So in that case, the direction is going to be pointing into your wrist. Now, I'm sure y'all remember our kinematic equations that we used for constant acceleration. Well, we have kinematic equations for rotational acceleration, okay? And so this table shows the comparison between the rotational and the linear. And you can see they're basically the same, except we use different symbols. Okay, so we're going to do some problems where we are going to be using those kinematic equations for our rotational constant velocity problems. Okay, so back to our compact disc. Okay, so we have this compact disc. It spins at variable rates between 500 and 200 revolutions per minute as it plays from the inside track to the outside track. CD contains 60 minutes of music. How many revolutions does it make? Okay, and now what we're going to assume that it would be a constant acceleration. So we want to find out what's our revolution. So we want to, oops, sorry about that. We want to find out what's delta theta. So our omega initial was 500 revolutions per minute. Our omega final was 60 minutes. And our delta t, oh, look what I did. Sorry about that. Our omega final is 200 revolutions per minute. And our delta t is 60 minutes. And we're looking for delta omega. Okay. So our formula that we would use to find this is going to be our delta omega equals 1/2 times omega I plus omega F times delta T. And even though it's not written, I did tell you that we were assuming constant acceleration. Okay. So now all we have to do is fill in our numbers. And so we have 1/2 times our 500 RPMs plus our 200 RPMs, and we're multiplying that times 60 minutes. So our delta theta is going to be 21,000 revolutions. Okay. Okay, let's try another one. So in this one, we have a circular drum of radius 40 centimeters. So we're given a radius to be 40 centimeters, is initially rotating at 400 RPMs. So omega I is going to be 400 revolutions per minute. It is brought to a stop, so delta theta is 50 revolutions. You're asked for constant angular acceleration, and you're also asked for stopping time. So what we want to do is convert our revolutions to radians and also our minutes to seconds. So in one revolution, we have 2 pi radians, and in 1 minute, we have 60 seconds. So that's going to give us 41.9 radians per second. And 50 revolutions. In 1 revolution, we have 2 pi radians. So we're going to have 314 radians. Okay. So now, when we look at our kinematic equations, the best one that we can use is going to be our omega final squared equals our omega initial squared plus 2 times alpha delta theta. Okay. And what we're going to do is we're going to solve that for alpha. So first thing we're going to do is move over our omega initial. So we have omega final squared minus omega initial squared equals 2 alpha delta theta. And then we're going to divide both sides by 2 delta theta. Okay, and then what we're left with is that alpha equals omega final squared minus omega initial squared over 2 delta theta. Okay. So alpha is going to equal 0 minus 41.9 radians per second. And that's all going to be squared divided by 2 times delta theta, which is 314 radians. So then alpha is going to equal negative 2.79 radians per second squared. Okay. And then we still have to find what delta t is. Okay. Well, we know that we look at our equations, we have delta theta equals 1/2 omega initial plus omega final times delta t. So I know everything in that equation except delta t. Okay? So my delta theta is going to equal 1/2. My initial, omega initial, is 41.9 radians per second plus 0 times delta t. So what we have is delta theta equals 41.9 radians per second divided by 2 times delta t. So we want to bring over and leave delta t by itself. So we're going to have 2 times 314 radians divided by our 41.9 radians per second. And that's going to give us delta t equal to 14.9 seconds. Let me put this little line because this quantity is not squared. That 2 right here is the 2 from this 1/2 when I moved it. So it's not that it's 314 squared. I don't want you to be confused. So 14.9 seconds equals our delta t. Okay? So this is the answer for the time. This is the answer for our acceleration, our alpha. Okay, let's do one more. Okay, in this one, we have a belt that is wrapped around the edge of a pulley that is 40 centimeters in diameter. So diameter is going to be 40 centimeters. The pulley rotates with a constant angular acceleration. So right away we know it's going to be a kinematic equation. And that alpha, that acceleration, is 3.50 radians per second squared. At t0, the rotational speed is 2 radians per second. So that tells us that omega initial is 2 radians per second. What is the angular displacement? So we want to know what's delta theta. And what is the angular velocity of the pulley 2 seconds later? So we want to know what's omega f given a time of 2 seconds. Okay. So let's find our angular displacement first. So we look at our kinematic equations and we see our second one would work for us. And that is when you have delta theta equals omega I delta t plus 1/2 alpha times delta t, and that's squared. So we have, why it's going this crazy line, sorry about that. So we have delta theta equals our omega I, which is our 2 radians per second times 2 seconds plus 1/2 times alpha, which is 3.50 radians per second squared times delta t squared, which is 2 seconds all squared. So when we plug all that in, we get delta theta equal to 11 radians. And now we want to know angular velocity of the pulley 2 seconds later. So we're looking for omega final. And again, we look at our sheets and we see omega final equals omega initial plus alpha delta t. So we have 2 radians per second plus 3.50 radians per second squared times 2 seconds. And therefore our omega final is going to come out to 9 radians per second. Okay, and again, I apologize for those lines that showed up as I was writing. I hope they don't confuse anybody. Okay, we're going to end this recording now, and we're going to call this part 1, and we will be back and pick up with torque for part 2 of our recording in chapter 8.